השעון ששם למעלה, עכשיו רק 12. מה, תקנו את זה? אתם רוצים להגיד? וואלה.
במיוחד בשבילך.
Okay, let's get started. It's a pleasure to have with us today Eran Vos. Eran did his undergrad in Tel Aviv University in Physical Science. Then moved to Weizmann Institute for Master in PhD. And he graduated about a year and a half ago and then moved to Paris to LMD. He's working there as a postdoc in topics related to Mars and other planetary science. Any questions?
Thank you, guys. Thank you, everyone. So, as Guy said, my name is Eran, and today I'm going to talk about mostly about Mars. It has a lot of relevance to Earth, mostly Antarctica and other planets, but this talk will be only focused on Mars. I will say some stuff about Earth during the presentation if I have some time. And the topic is the long-term climate change on Mars that is induced by periodic variations in the orbital elements. And we will talk a lot about the evolution of the Martian ice reservoirs in the late Amazonian, so somewhere about the last 20 million years. Please, if you have any questions that makes you don't understand the presentation, raise your hand and ask the question. We have enough time, it's all good, okay? So the outline of the talks is, first I'm going to give a brief introduction about Mars, since I know most of you work on Earth stuff. Then I will present the most simplest model I could make in order to capture the interactions between the icy reservoirs. Afterward, we will dig more into the details of what controls the North Polar Layer deposit physical and chemical stratigraphy. If I see we have enough time, I will discuss the relationship between the NPLD, the North Polar Layer deposit. I will say a lot the NPLD because it's much shorter. And the subsurface ice. And lastly, I will talk about the really, really cool project that was just submitted about why the mid-latitude subsurface glaciers are there, which have a lot of implication to Antarctica. We are currently also taking the novel approach we did for Mars to Antarctica to explain some stuff.
Number 5 is on Earth.
What?
So number 5 is on Earth.
No, all of this is on Mars, but this is very, very relevant for Antarctica. Then I will summarize, and if we'll have more time, I will discuss other project I'm working on, and we'll see how much time do we have. So, let's start with the motivation of this presentation, or my work in general. We want to be able to explain what is the climate change on Mars in the past, so we can project towards the future. So, on Earth, we drill ice cores from Antarctica or Greenland. We look on these ice cores, the isotopic ratios, and the accumulation rates, together with the orbital element, the precession of liquid, the eccentricity, and the solar. We can learn about the solar forcing and learn about the stages of glaciation, when it was warm, when it was cold, and know about the past climate. And many of you probably know that some of these are also extrapolated into the future to learn what will be the climate in the future. On Mars, we want to be able to do the same thing. Here what we see is the NPLD as seen from orbit. And this is a layer sequence seen in one of the troughs that is exposed. And of course, you all see that we have a lot of richness in this kind of record. And we want to learn what we can decode from this stratigraphy to learn about the climate. So some very basic introduction. we have the solar system, the Sun, Mercury, Venus, Earth, Mars is the fourth planet, and Jupiter, the gas giant, is the fifth planet, a very massive planet, gas giant that perturb and changes the orbital configurations of the planets. So the radius of Mars is just a bit more than f of Earth's radius. The gravity is about 40%. The day length is quite similar. The year length is almost twice as the year length on Earth. This is because the distance to the Sun is at 1.5 AU. You can solve Kepler equation and get the year length. The surface pressure, so the atmosphere, on Earth we have 1 bar or 1000 millibar. This is the surface pressure. And on Mars it's much thinner. The atmosphere is much thinner. It doesn't have big capacities at all. It's only 0.6%. This is of course an average and can change and changes during the history.
Only 0.6%.
0.6%.
Without Earth.
Yes, of course. So let's talk a little bit about the icy reservoirs that I'm going to discuss during this talk. This is the North Polar Cap deposits. We've seen this picture before, the NPLD is seen from orbit. If you look on the right on the layer sequence, I want you to closely look on the stratigraphy and see the richness. We have difference in albedo, difference in textures. For instance, here we have a much rougher layer. There's different thicknesses. Some layers seems to be about 20 meters thick, and some layers are packed 1 meter. And we don't really understand what controls this stratigraphy. Yes?
You said what you're showing on the right? This is a core that was taken?
No. So this is the NPLD seen from orbit, and you can see that there are troughs into the NPLD. And basically what you do, you take the camera, the Mars orbital camera, and you look into the trough. So it's a cliff, and you can see it from the side. Sorry, I wasn't clear enough. You can see it from the side, and then you can see the layers. You can see also that in this, it's tilted. This is because of the orientation of the trough. If you look at that different troughs, you see different orientation. And it's a very good question because what I show you on the left is we see a cross-section from the side of, as you look towards the cap, of radar data, and you can see that most of the layers are horizontal. Some have bending caused by this kind of trough. Okay?
What are the landscapes?
So the NPLD in diameter is 1,000 kilometers, and in thickness is about 2.5–3 kilometers, depends where you look. This, what you see here is 200 meters. I don't know if you see it, so it's quite extensive. It's not like a little feature. In the mid-latitude, we have the subsurface ice deposits. On the left, we see craters exposing ice. So a crater comes, it excavates the regolith, and you can see ice. And here we can see the Phoenix Lander landing site, who had like a spoon that took off some of the regolith to expose what seems to be like pure ice. This ice is only stable in the subsurface, below a lag layer that acts as a thermal insulator and a diffusion barrier, and I will discuss about it a lot later on this talk. This is a map, so latitude, longitude, and the blue region seems some kind of measurement of where we think we should have subsurface ice. So we can see subsurface ice extending from the poles to about latitude 45. Sometimes we find places near the equator. As more blue, it means you have more ice there. So how can we place ice in the subsurface? There are two options. The first is diffusion and the second is self-burial. Let's start with diffusion. We have the atmosphere, the soil, and in some kind of a Z we have ground ice. This is the temperature profile from the surface where you have a lot of variation between day and night. And as you go deeper into the ground, this variation decreases. If you look on this equation, we have the atmospheric water vapor over T self, the annual average. have the saturation vapor, which is a function of the temperature, in some kind of Z, in some kind of that over the temperature, the annual average. If this equation is satisfied, water vapor can diffuse through the pores in the regolith and drop in the ground ice. If this equation is not satisfied, if you have ground ice, this ground ice is retreating and ice vapor goes into the atmosphere.
What's the basis for it?
Just thick law. You have a medium, you can pass vapor through.
So you know what the diffusivity constant is? Or?
Yes, it's quite easy to calculate. We have measurements.
This is based on the diffusivity constant.
Well, this is just tells you if it's growing or not. This is the term that tells you if you have growing or decreasing. When you want to look at the flux, you have diffusivity and many other parameters, which I will introduce a bit later. This is just tells you if you're growing or not. So basically, if you have more vapor in the atmosphere, it goes in, and if you have less vapor, it goes out. It's quite simple. The other option to have subsurface ice is a self-burial. So here we have air, ice, and regolith. And if this ice is lost, this ice has a certain amount of dust. So the ice is lost, it sublimates only the ice, and the dust left behind. So we can grow a log on top of the ice. So the Z log size is the flux times the ice dust fraction, and as you keep growing the log there. We also find some geological evidence in the near equatorial glacial deposit, where, for instance, here we can see evidence of ice flow in the flanks of Tarsis. So, how overall Mars look like? On both poles we have the polar caps, the NPLD and the SPLD. The NPLD is much larger and much younger, assumed to be about 5 million years. The SPLD is about 100 million years. We can learn about it from the roughness and the crater we can see on top of them. They are growing on the vertical dimension. In the mid-latitude we have subsurface ice, which grows on the horizontal direction, and a little bit in depth, but it's negligible. In the tropics we have evidence of this glacial flow on flanks of volcanoes, but this is very poorly constrained because we only see evidence, we don't know the amount, and we are also working on this to understand the atmosphere is well mixed, much more mixed than on Earth, so I won't discuss that because I don't have a lot of time, but if anyone is interested in the cells on Mars, I will be very happy to talk about it. So what's inducing this transfer from one icy reservoir to the other, and what controlling is the orbital variation. So from top to bottom we have obliquity, eccentricity, and longitude of perihelion. On the x-axis we have time in million years. So let's start with obliquity. Obliquity just tells us the angle between the rotation axis to 90 degrees. We can see that the obliquity about 10 million years ago were between 25 and 45. However, about 5 million years ago, we see a drop in the obliquity. The mean drop for about of 35 to 25. The time scale of obliquity is about 120 kiloyears for this cycle, and for the entire envelope is about 1 million years. The eccentricity also changes a lot, from almost circular orbit to 0.12, which is very eccentric. The time scales are 100 kiloyears and 2 million years. The longitude of perihelion tells us if we have an eccentric orbit, at which location we are at perihelion, the closest approach to the sun. And this can be very important if we have eccentricity of 0.1, like today. The difference in extremity of the summer, if you're at perihelion or at aphelion, can be twice as large. I forgot to say that today's obliquity is about 25, similar to Earth. Earth is 23.5. However, the variations in obliquity is about 20 degrees, that on Earth is only about 21 to 25. This is right on.
24 and a half, 22 and a half.
Yeah, so 2 degrees, so 10 times larger. If we have all of the orbital configurations, we can compute the insolation at summer solstice at latitude 65. And this is what we see here in watts per meter squared as function of time. We can see how nicely it follows the obliquity cycle. The dashed line in the middle represents at times where the ice is stable in the polar region. So above the line, ice is not stable in the polar region, and below, ice is stable in the polar region. And we can see that when the obliquity drops, ice is much more stable in the polar region. And this is the time we think the NPLD was formed. However, there's other things we consider now. Maybe it was only halfly grow this time, but this is like really detailed and I won't talk about it today. So basically what we want is yes?
Let's just go back to obliquity. So obliquity should be stationary, right? So it should change, but the median should be constant in time.
No.
This is obliquity on Earth is how this works.
Yes, but you know why obliquity on Earth is so stable? We have this giant moon sitting outside, which holds so much angular momentum in the system. So every little turn you want to do to the obliquity on Earth, you also need to move and add a lot of angular momentum to this system. And this is why it makes the obliquity so barely shifts. On Mars, you don't have this, so everything Jupiter do changes Mars orientation.
So this shift at 4 million years ago is something which is modeled and comes out of what? Like, how do you know that there's a shift?
Honestly, it's quite easy to do it. All you do is you start with present day status, and you do an n-body simulation of the solar system. And of course, this is chaotic, but it's chaotic about 20, 30 million years ago. From 20, 30 million years ago. You run all of the initial conditions you can try, and in the last 10, 15 million years ago, less 10 million years ago, it's all giving the same results. It's a quite simple n-body simulation. You run it with Mercury.
What do you mean N? You take
All of the planets.
all of them, including the
Well,
inner ones?
after Saturn, you don't really care for Mars, but you
But
saw.
the inner ones?
Yes, you need the effect in Mars. If they go out and they are getting closer to Mars, they're perturbing it also, right? It's a function of distance and mass. Yes?
Are these calculations done by the same group, the Lascar?
Yes, it's Lascar.
So it's the same. Is
It's
it the
Lascar.
same product out of the Lascar?
Yeah, it's Lascar 2004. It's the same one everybody uses for Earth.
Yeah.
I even, the guy I told you that is weird and told me, why you don't speak French? This is Lascar. Jacques Lascar is a really big character, but he's a nice guy and he's the one who's doing these calculations. Well, I also did it for myself, not in the same accuracy to make sure this is correct, but it's pretty consensus.
So the reason for the shift is interaction with Jupiter?
Yes.
One last question. The precession on Earth, there are two different precession cycles that we'll talk about.
Yes.
One which is this one, another one is the wall.
Yes. We have it on Mars also, but it's less significant. This one is really significant because we are very eccentric. So when it's very eccentric, it's really important which hemisphere is pointing the sun at which time of the year. So you can have a very short and extreme summer or a very long and mild. So of course, also we have the other orbital parameters, but these three are the dominant. Okay, let's move on. We'll have many times for questions, and I will stay here about until like 4. So if anyone is interested in this specific orbital variation that I'm not an expert about, can ask me whatever you want. So basically what we want is we want to explain geological observations, and we want to be able to look at this geological observation and explain what was the climate that formed them. So we see some ancient terrains of water flow, which assumed to be water flowing on Mars about 2 billion years ago. We won't talk about it. It's a different project completely that I'm involved in. We see some glacier flowing, and this is assumed when the obliquity was a bit larger. I will explain this in details later. We see some CO2 ice glacier moraines on Mars in the polar regions. We think this is at times when the obliquity was low, almost 15 or even sometimes 12, which collapsed the atmosphere into the poles because no insolation reaches the pole at these low obliquities. When I say no, it means minimum. And it's so cold that CO2 becomes trapped in the poles. So you build those giant CO2 glaciers that creates these moraines. And then we have the North Polar Layer deposit, which I discussed so much, and we have these stratigraphies that we want to explain. And we believe that in this stratigraphy, we can see all of the glaciers and the CO2 ice glacier moraines. So, just to give you an example, and so you can believe me before I continue and give you harder stuff to believe in, that these icy reservoirs are controlled by orbitally driven ice distribution. I put ice in the poles like it's at today. I change the obliquity to 45, and I let it evolve as time. LS is the solar longitude, it's just the way to look at time. LS90 means north and summer. LS270 means southern summer. So you can see as it evolved, ice moved from the poles to tropics. This is where you have Tarsis Rise, where you expect to have, where you see glaciers. You also have a little bit in Elysium. And basically, this is what controls the movement of ice. So, at the beginning, what we wanted the simplest model we can that can capture this interaction between the reservoirs. So, it's called the three reservoir model. We have the NPLD. We take the fluxes from GCM simulations. We have the mid-latitude. We compute the equilibrium ice table, and it moves on the horizontal, while the NPLD moves on the vertical. And we have the equatorial glacier deposits, which acts as a mass conservation. So if two reservoirs are gaining, the vapor comes from the tropics. If one is gaining and one is losing, what's left comes from the tropics. We also calculated, we assume the atmosphere is male mix, which is a really good assumption.
It's very thin, is it 60 meters?
What's 60 meters?
The thickness of the atmosphere.
Our thickness?
On Earth is about 10
This is
kilometers.
so the scale height is similar.
6 per mil.
The scale height on Mars is between 10 kilometers to 12 kilometers, but the topography changes a lot. So you have 16 kilometers between the northern hemisphere. 16 is the maximum, let's say. 10 kilometers difference between the northern hemisphere and the southern hemisphere. So, of course, you have the thickness of the atmosphere is about 60 kilometers, which you still have dynamics because you don't have a stratosphere.
60 kilometers?
Something like this. Don't catch me by the exact number. But the massive dynamic occurs on the 10 kilometers. This is the scale height.
The gravity is a little small. The gravitational constant is a lot smaller.
Gravity is a fourth.
Okay, we continue and we can discuss it later in the questions if you prefer. So we also calculate the isotopic ratio for this model, the fractionation weighted. It looks complex, but basically what he said is the isotopic ratio of the accumulated ice is weighted by the fractionation coefficient alpha, which is a function of temperature. Colder temperature will lead to higher fractionation, and the flux. So if one reservoir is losing and two reservoirs are gaining, we get okay, I'm going to jump a bit forward a little bit after this. So you get isotopic accumulation in the polar region, and if two reservoirs are losing and one is gaining, the sum is just the average. So we can look at our we ran the model and we can look the reservoir volume in meter in global equivalent layer as function of time. In green we have the glacial deposit, in blue we have the NPLD, and in reddish we have the subsurface. The first thing is easy to see is that the NPLD grows on the expense of the glacial deposit, and this is very cool because this is what we see. There are times when the obliquity is low and almost constant when we have a monotonically grow. It looks like the subsurface doesn't play an important role, but if you look only on a layer formation timescale, all three reservoirs interact. We can look at the NPLD, how it may look if we had an ice core. So we plot the NPLD as function of depth. So this is what we have on the left y-axis, depth and time, and of course we have it's not a linear relationship between accumulation and time. I won't discuss this a lot because I want to jump. I want to have time to talk about the new project. Basically, what we can see is that we have in the white is the accumulated layers of ice, and gray are dust lag layer left behind when this ice sublimate. And we can see that we have two different regimes. One, when we have ice growing monotonically, and another regime when we have sublimation lags leading to unconformities. And we were very happy with this result because we can see and explain some main dominant feature we find in the NPLD, like the different regime, the different thicknesses. I'm going to continue. But honestly, when we ran this simple model, we knew that we are missing a lot of physics. Cloud condensation, sedimentation, sublimation from the surface, the way the microphysics interacts with the sunlight. So what we did is we collaborated with LMD, the Laboratory Meteorology Dynamic, where I'm doing my postdoc currently, to work with them with the global climate model. So we wanted to dig in the details to understand what controls all of those important features. I'm not going to talk about this. This is just show a comparison between data and GCM simulation. So now that we have this very strong tool called the Global Climate Model, we can look very specifically into features like the accumulation rate of the NPLD as function of the dependence on the orbital elements. So this is the first thing we've done. We have LP and obliquity. This is the perihelion alignment. And the color coding is the North Polar flux in millimeter per Mars here. We can see it somewhere between 1 and 5. And this is the sweet spot where we have the most accumulation. It was a kind of surprise risk for us. Why was 25? Today we are here at 25 and 251. In 50 kiloyears we will be here. So we wanted to know why? Why 25? And after a little bit of thinking, it makes sense because, of course, if the obliquity is very high, we already seen before, a lot of insolation reach the polar region, and I sublimate, so of course this won't be the location where you have the most accumulation. However, if you look at latitude 15, you're starting to make CO2 glaciers. It's very cold in the poles. You have CO2 glaciers that pins the temperature to the frost point of CO2, which is 145 Kelvin, approximately, depending on the pressure. And at this regime, you cannot push a lot of vapor into the poles because it's so cold. Wherever you push a bit of vapor towards, the temperature makes the particle condense, and it drops instantaneously. And we find that this is the sweet spot, 25. We also wanted to know the flux as function of surface ice migration. So we put ice in the tropics, so we have latitude and the amount of ice. The color coding tells us the amount of ice transported towards the poles. So at the beginning, the bluish, most of the ice is in the tropical mid-latitude, and reddish means almost all of the ice is already in the poles. The black represents the initial condition, and we can see that as it evolves, first it moves to a very specific location in the mid-latitudes and in Tarsis, and a little bit to the poles. However, later, when no more ice is left in the tropical region, this mid-latitude becomes the source. Yes?
So in your model, it's just like a thermodynamic ice, or you're just counting like where there's accumulation of ice, and you're not there's no like actual model of the ice itself. Like there's not like a dynamic.
No, there is. It's a
Okay,
global climate
is it a
model.
thermodynamic ice, or are you using?
Of course, it's completely a self-consistent model. A global climate model solves all the
Yeah, but then I'm
equations.
saying, what's your ice sheet model within the GCM?
I have an ice sheet model in the GCM. If I have ice,
Yeah, so is it a thermodynamic ice sheet model?
you look at
or
this
is
from
it
a
like
point of view of Earth. On Mars, if you have ice, the thing this ice is doing is changing the thermal inertia of the surface. It doesn't grow or push stuff away. It's just growing on the surface or decreasing.
How do you know it's not pushing stuff away?
Because it's very thin. You can see it's millimeters. You have like 3 millimeters or 4 millimeters of ice.
I thought you said the caps.
The caps are 2 kilometers thick, but in a very small region. If you look into the area size and you calculate also the area size, you find that the mid-latitude glaciers are not very thick.
Okay.
Meters maximum.
Okay, but at the poles they would be dynamic.
Yeah, in the poles they are dynamics, they can flow, they can do whatever they want.
Okay, but your
Not
model
on,
doesn't have like a dynamic ice sheet.
not this model, but it's a good question because we developed a new approach which has the dynamic. This one is on a yearly timescale. This entire simulation is 200 Mars years, which took like 3 months of computer. So at this time you don't really have flow. But remind me the question when I reach the present project we do. We actually faced a lot of trouble calculating the flow and stuff like this because the way they interact with the ground is different because it's all cold based, and I will talk about it later. Okay. So we also calculated the isotopic ratio for this. The contours are exactly the same. However, the color coding this time is only the isotopic ratio. So you can see, for instance, let's look at the SPLD. It starts blue and changes to red. This is because the sources of warmth changed. And it's easier to see it if we look on a polar isotopic profile. On the y-axis, we have the fraction of ice transported. The x-axis tells us the isotopic ratio for the North Pole and for the South Pole. Each circle represents 1 year of GCM simulation, and the dashed line represents the mean of the isotopic ratio of this pole. So, at the beginning, when ice was in the tropics and moved most to the mid-latitude and the poles, we have a depleted isotopic ratio. This is easy to understand because as ice sublimated from the tropics, it reached the clouds, it was enriched, reached the mid-latitude, reached a location which it condensed all the enriched isotopic ratio, and the atmosphere, the air that kept pushed to the polar regions was already depleted. So we have a depletion. However, when this mid-latitude becomes the source, we have a giant jump in the isotopic ratio because the source was already enriched. It's completely different than on Earth because on Earth you have this giant ocean where the isotopic ratio is pretty constant, and every water that sublimate, the source is the same, so it's only a function of the cloud height or the transport into the inland. However, on Mars, where you don't have this constant pool of isotopic ratio, the source reservoirs plays a very important role. The last thing I want you to look in this plot is that the top layer is more enriched compared to the average annual in both poles, and they are different. So, until 5 years ago, people look at the D2H ratio of the atmosphere of Mars, and from this they extrapolated what is the loss of ice or water throughout Mars history. So the value is about 4.5, and they assumed, okay, we see this amount of ice, it's 4.5, it means we lost 5 times this amount. Of course, this is just However, after we published the paper, many of the authors of those extrapolation came and talked to me and said, okay, so what do you think? What's the, and I told them, the layer you see that is only in contact with the North Polar layer deposit, the highest point on the highest layer is not representative. You need to be able to extrapolate all of this. So they changes the values and gave a much bigger range, and we were happy about it. And I'm not going to talk about this project because I don't have time. I will just put this one. It's a very cool project, it's too bad, but I'm just going to put this slide. Is it running? No? Okay, so here we see the orbital variation as they change, and here we see the depth to the subsurface ice, latitude, longitude, and the amount of ice. So I squeeze all of, I sum over the z to get the amount of ice. Basically what I want you to see is that the subsurface ice changes a lot. I think it's the most beautiful plot I've ever done, and I would never do a more beautiful one. It was for my PhD, and I did like, I think I spent only on this plot like for 4 hours or something like this. So basically what we see is we can see that the subsurface ice is breathing towards the tropics at high obliquity and retreating towards low obliquities. There's a lot more to see here. We can see that where it's continuously stable, the amount of ice is large, and at places where we don't, where it grows and retreats, we have a very small amount of ice. And I will just let you see it until the end, and you can feel the breathing.
What depth is this?
You can see it. Sorry, you can see it here in the side. So oranges are a few centimeters, and blue is about 8 meters. Don't look at this. This is the amount of ice. Here, blue is a lot of ice. So, few centimeters. Of course, as you go towards the equator, it's deeper latitude, deeper depth. So I will let it finish so I can show you the last what we think is today. So this is only pore ice growing. It's only through diffusion. We don't have glaciers here. And this is a present day pore filling, and this is a very good agreement with observation. We see that it's up to about latitude 55, a little more if you look at the deeper depth. We have some variation in the longitude, but if you remember at the beginning, I showed you that people find in observation ice all the way to latitude 40. So who's right? Who's right? The models, the observations, people who do models as me, I would say, listen, this model is, I'm sure is correct. However, people who are colleagues of me and show me, look, I can see ice. And I say, yeah, it's ice, of course.
Don't confuse me with the facts.
Yeah, don't make my model look bad. So, there is an option that both are right. Okay? I'll skip this. So we can see that this is the blue is where we find ice in craters, and red is not. This is the crater diameter, and this is the depth of the ice as a function of latitude. And we can see that if we go from the equator towards, we have a decrease. So at latitude 55, we find the spore ice at about 10 centimeters. However, if we look to latitude 45, it's about 50 centimeters. So there is an option that both the models and the observation are right. This is if this ice is ice that was glaciers in the mid-latitude that slowly retreated. However, models that tried this found that ice should be in about 2 meters deep, which is not consistent with observation. So we wanted to attack this. It really bothered me that my model doesn't agree with the observation, because what to do with models that don't agree with observation probably are wrong. So we, in order to attack this question, we developed a new kind of climate models. So what I left you with the the tension between the model. This is how I finished my PhD, and I started my postdoc, which I already knew what I'm going to do. I developed a new climate model called the planetary evolution model, which basically what it does, as you asked, is asynchronously coupled with this global climate model. So how does it look? We run the GCM for a few years with a time step of 1 minute. We calculate the evolution of the accumulation rate, the condensation rate, the evaporation rate, and we call this Mars planetary evolution model, which compute and extrapolate the ground ice evolution, the glacier evolution. It also do hydrology, but I won't talk about it today. Until it reached some kind of stopping criteria. An example for a stopping criteria, I changed more than 5% of my glacier in size, which I need to call the GCM again to get new tendencies and so on. I'm still developing it. So we needed to build a lot of new schemes into the GCM. For instance, the lag deposit model, which I'm going to talk about it now. Basically, in the GCM so far, we either have ice on the surface or no ice on the surface. There wasn't an option of subsurface ice that can slowly sublimate. So this was my first project. I also did a dynamic porous evolution model. I'm not going to talk about it. And glacier model, the way the glacier flow on the surface on long time scale. I also calculated a hydrology model. I'm not talking about this today. So this lag deposit model, basically, this is how we developed it. We have air, lag, and ice, and we want to know what is the flux between those. We built this very sophisticated implicit scheme. I calculated, I was back to first degree, calculating equation on like 7 pages long. But eventually what we find is that the flux, this is here, the flux is a function of the surface pressure, the drag coefficient, the wind, the amount of vapor in the atmosphere, the depth of the lag layer, and the diffusion coefficient. And you can see that the flux is a function of 1 plus 1 plus R, called the resistance, which gives, this is the resistance. If anyone is interested in this implicit, very beautiful scheme, I will be able to share it. This is what we also do now for dry ice in Antarctica. And this is what we see here. We have the subsurface ice flux reduction factor as function of depth of the lag layer. How thick is the lag layer? And we can see that the flux drops really quickly. So about after 1 meter, we drop in 2 orders of magnitude. So how this lag layer model plays, basically the GCM looks, I have a surface frost. If I have surface frost, perfect. We go back to the old scheme. Ice interacts with the atmosphere, and we added a new scheme of the subsurface ice below the regolith interacting with the frost. No, I don't have frost. Okay, do I have subsurface ice? Okay, I have subsurface ice. The subsurface ice interacts directly with the atmosphere through the pores. And here I show some results of the simulation. I show latitude 45 for present day orbital configuration. This is the depth, this is the surface, and this is deep. And this is the loss rate of the glacier in millimeter per Mars. And I plot here 5 different humidities, and we can see very nicely the drop of 1 over 1 plus R. Of course, higher humidities mean less loss rate. We see that in this kind of stuff we lose about 4.5 millimeter per Mars year. We can do the same thing for different orbital configuration. This is what I plot here again, depth, ice for different orbital elements. And you can see that different orbital elements, because the amount of insolation reaching the surface is completely different. So we can see from, I don't know, -9 to about -3, so 3 times lower. And I didn't do any extreme years. I also have obliquity 15 and obliquity 35. It can be about order of magnitude different. And again, as we go deep, we have this loss. It's not easy to see, but sometimes it's also accumulated. So basically, I have the loss rate at latitude 45 as function of humidity and as function of orbital elements. Basically, all I need is an initial point to start where the glacier was formed and the humidity history, and I can calculate the subsurface glacier depth. And of course, this is what we did. First, we calculated the humidity. This equation, this plot looks simple, but we needed to completely change the scheme of the microphysics, because in higher obliquities, the interaction to the humidity is much higher, and different clouds are forming. Let's leave it aside. It took me a lot of energy to make this plot. So we have humidity on the y-axis in a log scale as function of time in kiloyears. 600 kiloyears ago, obliquity was 35, and we had about 300 perceptual microns. When the obliquity is low, 18 here, we had about 2 perceptual micron. This is present when the obliquity is almost constant, moves somewhere between 20 to present day, which is 10. So all we are left is to know is the initial condition. I won't talk about this plot. Basically what we see is we see ice accumulated in the mid-latitude for obliquity 35 and LP90. The last time it happened when we had this is 630 kiloyears ago. This is why we chose this initial condition, 630 kiloyears ago. And we can see the glacier depths get increasing with time. This is present. For different dust scenarios, observations suggest 0.5 is the best option, even less, 0.4, 0.3. And basically what we see here is we see the glacier getting buried on himself from loss of subsurface ice. And we just submitted it like 2 weeks ago, and we were very happy because we finally could solve this tension and this enigma if the models are right or the observations are right. And we are working with people from observation now, so they can run our model and see if the glacier depth they find is the right one. And this is also people from Earth take it to dry valleys in Antarctica and implement it in their own GCM. So just a quick summarize. We showed that the physical and chemical signal should be present in the LPLD. I didn't talk about the chemical signal because I didn't have time. We characterized the MPLD accumulation rate and found that the migration of ice from the tropics to the MPLD occurs at 2 stages. One, first to the mid-latitude, and afterwards from the mid-latitude. I didn't discuss this at all. I didn't discuss this. And our last project we just submitted is the solving the enigma of the subsurface mid-latitude ice on Mars. I will talk like 3 minutes about other projects and then we can take questions. It's okay? Okay. So other projects I'm involved or leading or some of my students did. Some observations show that the humidity seems to be larger on present day at different times, mostly in the 70s. And we concluded that it can be if the CO2 cover, the perennial CO2 cover from the SPLD is gone. I didn't discuss it at all, so it might sounds very weird to you. High obliquity exclusion, so we want to explain the regimes when we see ice, lag layer ice, and we want to be able to quantify the thickness of the lag layer. Dunes as proxy of past dust loading. We are looking at dunes and we are trying to, using the GCM, trying to understand if the orientation of the dunes and the way dunes look tells us about the past dust cycle, which is another huge enigma. We improve the microphysics to have better clouds, and from this we get these glaciers in the mid-latitude. This is really cool. It's something I do with Paul Ain from Colorado University. We want to look at how global dust storm affects the next years, and we see like a really good agreement between models and observation. We want to see if we can find liquid water on high obliquity epochs like 330 kilometers, which the result so far, this is led by Lucas Nunn, one of my students, and it seems very surprising. and we want to build those CO2 massive glaciers at low obliquity